Ever wondered why your digital devices work so flawlessly? Sequential logic design plays a crucial role in it. Today, we're going to explore the foundation of how digital devices operate. Sequential logic design. This is a critical aspect of digital design, enabling our devices to carry out complex instructions and operations with remarkable precision. Sequential logic design is all about circuits with memory, where the output depends not just on the present inputs, but also on their past. This is what gives digital devices their intelligence, allowing them to remember and process information. One of the pioneers in this field is David M. Wakerly, known for his seminal contributions to digital design. His teachings have been instrumental in shaping the understanding and application of these principles. From the fundamental building blocks of sequential circuits to the broader digital system design methodology, we'll cover it all. So, are you ready to dive into the fascinating world of sequential logic design? Sequential circuits, the heart of digital devices, rely heavily on memory elements. These circuits are fascinating creatures of the digital world. Unlike their siblings, the combinational circuits, sequential circuits have memory. That's right, they remember. They store information, and their output is not just determined by the current inputs, but also by the information they've stored. Now, you might ask, how do these circuits remember? The secret lies in their components, the memory elements. The most fundamental of these elements is something we call the flip-flop. Yes, just like the footwear. But these flip-flops are less about comfort and more about function. Flip-flops are the building blocks of sequential circuits. They're the ones that store and manipulate binary information. If you imagine sequential circuits as a digital library, then flip-flops are the books holding the information. There are various types of flip-flops used in sequential circuits. First, we have the D flip-flop, also known as data flip-flop. The D flip-flop has a property where the output equals the input, which is why it's often used for storing binary data. Then we have the JK flip-flop. It's like the Swiss Army knife of flip-flops. It can function as any other type of flip-flop, making it incredibly versatile. Last, but certainly not least, we have the T flip-flop, or the toggle flip-flop. This little device toggles its output on each clock cycle, making it great for binary counters and dividers. So let's recap. Sequential circuits are like digital libraries. They remember information thanks to their memory elements, the flip-flops. And these flip-flops come in different types, each with their unique properties and functions, helping the circuit store and manipulate binary information. So the magic behind the memory of your digital devices is largely due to these flip-flops. Ever thought of communicating the behavior of circuits? State diagrams and state tables do just that. They're like the secret language of sequential circuits, helping us map out the complex paths of information flow. State diagrams are visual representations of the states in a circuit. Picture them as a network of nodes, each node representing a state. The transitions between these states, triggered by clock pulses or external events, are represented as arrows. It's almost like a game of hopscotch, where each square is a state and the jumps are transitions. On the other hand, state tables are tabular representations of the same information. They offer a clear, concise way to present the state transitions in a sequential circuit. Each row corresponds to a state, and each column represents a potential next state or output. Now, isn't it fascinating how we can represent complex circuit behaviors using diagrams and tables? Simplicity is the ultimate sophistication. This holds true even in sequential logic design. Let's delve into the realm of state minimization and state assignment, two crucial steps in the sequential logic design process. State minimization, as the name suggests, involves reducing the number of states in a sequential circuit. But why do we want to do this? Well, by minimizing the number of states, we simplify the design. This simplification leads to a reduction in the number of flip-flops required, resulting in more efficient and compact designs. It's like decluttering your room. Fewer items mean less mess and more space. Now let's imagine you've successfully minimized your states. What's next? It's time for state assignment. This process involves assigning binary codes to the states in your sequential circuit. Consider it as naming your states, but instead of conventional names, we use binary codes. Why, you ask? Well, binary codes are the language of digital systems. They help us translate the behavior of our circuit into a form that can be understood and processed by the system. The effectiveness of state assignment can have a significant impact on the logic of the circuit and consequently its complexity. It's like solving a puzzle. The way you arrange and connect the pieces can either simplify the solution or complicate it. So careful thought needs to be put into state assignment. An effective assignment can simplify the logic, reduce the complexity of the circuit, and make it easier to understand and troubleshoot. But remember, there's no one-size-fits-all approach to state minimization and assignment. Each circuit is unique, and what works best will depend on the specific requirements and constraints of your design. So don't be afraid to experiment and explore different strategies until you find the one that works best for your design. Remember, a well-assigned and minimized state can lead to a more efficient and compact design. Ever heard of Mealy and Moore machines? No, they are not some fancy devices but key concepts in sequential logic design. Let's dive in. Sequential circuits can be broadly categorized as Mealy machines or Moore machines. This categorization is based on the timing of output changes. In a Mealy machine, the output depends on both the current inputs and the current state. This means the output can change as soon as the input changes, even within the same clock cycle. On the other hand, Moore machines are a bit different. Their outputs depend only on the current state. This means the output can only change in response to a clock edge, not immediately when the input changes. In essence, the difference between the two boils down to when the output changes. Instantly with inputs for a Mealy machine, or only at clock edges for a Moore machine. So the next time you hear about Mealy and Moore, remember they are not machines, but critical concepts in sequential logic design. Designing a circuit is just the beginning. The real challenge lies in its testing and debugging. The art of designing sequential circuits is not just about sketching a flowchart or drawing a diagram, it's about ensuring that the circuit works flawlessly when implemented in a real-world device. Every circuit, be it a simple flip-flop or a complex state machine, requires a well-thought-out clocking strategy. Clock signals are the heartbeats of our circuitry, triggering state changes and controlling the timing of the entire system. Without a proper clocking strategy, a circuit can behave unpredictably, leading to significant complications. Yet, even with the best clocking strategies, hazards and glitches can still rear their ugly heads. These are undesirable effects that can cause a circuit to malfunction or behave erratically. Hazards may occur due to timing issues or logic design flaws, while glitches are typically short-lived and may occur even when the system is functioning correctly. Engineers use various design techniques to eliminate or at least mitigate these issues, ensuring that the circuit performs as intended under all circumstances. Once a circuit is designed and implemented, it's time for the real test, validation and debugging. This is where the rubber meets the road. Every sequential circuit, no matter how well designed, must be rigorously tested and debugged to ensure its correct functionality. Testing strategies and simulation tools are employed to verify the circuit, identify any faults, and rectify them. Debugging is a continuous process, a quest for perfection that never truly ends. The art of sequential circuit design is a journey from concept to reality, from design to testing. It's about transforming an idea into a functioning circuit, a circuit that can be a part of a larger system, perhaps even a part of a device that changes the world. So this was a quick tour of the fascinating world of sequential logic design principles. Remember, a well-designed circuit is the secret behind every flawless digital device. We've covered quite a bit of ground in sequential logic design, haven't we? From the fundamentals of sequential circuits and the pivotal role of flip-flops, to the insightful use of state diagrams and state tables, we've delved into the essence of how information is stored and manipulated in digital design. We've also explored the art of state minimization and state assignment, which aids in creating efficient and simplified designs. You've learned about Mealy and Moore machines, and the unique output dependencies that set them apart. We've touched upon the synchronous and asynchronous sequential circuits, and how clocking strategies and keen attention to hazards and glitches contribute to reliable circuit operation. Finally, we've wrapped it all up with a look at the broader digital system design methodology, the importance of rigorous testing, and the need for thorough debugging to ensure correct functionality. And with that, we conclude our journey into the world of sequential logic design. Until next time, keep exploring and keep learning.